Hello class, for this video we will discuss binary trees and the binary search tree. So a binary tree is a tree structure whose nodes have at most two children. Okay, so here's an example where you have the root node here with value or key equal to 1, and it has two child nodes, and in turn they have at least uh, or at most two child nodes. Okay, so there are different types of binary trees, and these are special cases of binary trees. A complete binary tree is one where all the levels are completely filled except though possibly the last level, and the nodes in the last level are as far left as possible. So here on the leftmost part, kita nyo, it's a binary tree. Uh, all the levels except the last level are completely filled. Okay, meaning there are exactly two child nodes. Okay. Uh, Another type of binary tree is a full binary tree, where you have all the nodes of the binary tree possesses either 0 or 2 children. Okay, all the nodes. Okay, so even it's either 0 or 2, right? So as you can see, here's an example in the middle. Okay, you see a full binary tree. Okay. The last one is a perfect binary tree. Ito naman, it's a full binary tree, a special kind of full binary tree. All the nodes contains exactly two children other than the leaf nodes. Okay, so exactly two child nodes. Okay, except for these leaf nodes na walang child nodes. Okay, so a special case of a binary tree is when that binary tree is used to store the key values in some kind of order. Okay, so and this is what you call a binary search tree, and it's a node-based binary tree data structure, meaning you store the information on a per node basis. Okay, and it has the following properties. The left subtree of a node contains only nodes with keys lesser than the node's key. Okay. On the other hand, the right subtree of a node contains only nodes with keys greater than the node's key. So, and is also applied recursively, meaning the left and right subtree of each and every uh, node in the binary tree must follow this property. So as you can see, you look at all the key values on the left subtree of 8, they are all less than 8. Right? So, ito naman, all the key values in the right subtree of 8 are all greater than 8. Okay. Now, the binary search tree is used a lot. And you have and it when it's implemented, there are several operations that you use on the binary search tree. Number one, since it's a binary search tree, one is to search for a particular key value. So how do you perform by BST search? You start from the root and then compare the searching element with each node starting from the root, and then traverse or recurse either the left or the right subtree depending on the value resulting from the comparisons. For example, if we are searching for the key value 7, we compare it starting from the root node. Is 7 less or greater than 8? So since it's less than 8, it has to be in the left subtree. So now we go to the left subtree and compare it again with the next node. Um, the key value here is 3. Is 7 greater than or less than 3? So since it's greater than, we have to traverse and go to the right subtree, and so on and so forth until we arrive at a leaf node. So if that value is found, then the function will return a found value. Otherwise, if you reach the leaf node and you did not find that value, then it's a search miss. Okay. So how do you insert values into BST? So um, so here's how you do it. A new key is always inserted at the leaf. Okay. So we start searching a key from the root until we hit a leaf node. Okay. So since we are inserting the value and we just attach it to uh, as a leaf node, we just compare the value of the element that we want to insert, and then see where the leaf node is available so that we can add it as a leaf node. Okay. So once a leaf node is found, then you add it as a child of that leaf node. For example, here, if you want to insert 40 into this BST, we compare 40 with the value of 100, since that's the starting point, start from the root. We have to insert it in the left subtree. Is 40 less than or greater than 20? It's greater than, so go to the right subtree. Now, then we determine that 30 is a leaf node, so, and we compare the value of 40, is it greater than or less than 30? It's greater than, so we attach it as the right, okay, child node of 30. And okay, so how about BST deletion? There are three options here. And I leave it up to you to look at this and analyze. So one is where the node to be deleted is the leaf node. Is a leaf node. You simply remove it from the tree. So it's the simplest case. Number two case is that the node to be deleted has only one child. So in this case, you copy the child to the node and delete the child. Okay. So in this case, for example, we want to delete 30. 30 has only one child node, so we move 40 to the location of 30, and then we delete 30. So we end up with this BST. As you can see, the binary search tree property is still maintained. Okay. Now the most complex one is when you have when the node that to be deleted has two children. Okay. So this is more complex. So what we do is find the in-order successor of the node. Okay. So it means that we need to perform some kind of in-order traversal, okay, and determine the in-order successor of the node, because in what this is saying is that kung meron kang successor and then you delete that node, then that successor has to replace the current value. Okay. So, and then once you find that in-order successor, you copy the contents of the in-order successor to the node and delete the in-order successor. Okay. Note that we can also use the in-order predecessor, pwede rin. In either case, it will still maintain the binary search tree property. Okay. The important thing to note that is that in-order successor is needed only when the right child is not empty. Okay. In this particular case, the in-order successor can be obtained by finding the minimum value in the right child of the node. Okay, right child of the node. So in this case, if you want to delete 50, okay, what is the in-order successor of 50? Meaning, what's the, if you traverse this binary search tree, what key value comes after 60, after 50? Then, as you can see, it should be 60, right? So you put 60 there and you delete 50, and you end up with this binary search tree, which maintains the binary search tree property. Okay. So in terms of time complexity, The worst case time complexity for search, insert, and delete operations is O of H, where H is the height of the binary search tree. In the worst case, we might have a very skewed tree, meaning it's just a left subtree. There's no right subtree, or a right subtree pero walang left subtree. And that is the worst case. So in that sense, H might be equal to N. So the time complexity in that for search, insert, and delete could be O of N. Okay. However, if we can have a more balanced binary tree structure, and by balance we mean that meron siyang left and right subtree, and the difference between the heights of the left and the right subtrees cannot be more than 1 for all the nodes in the tree, then we will have a shorter height of the tree, and that will improve our time complexity. And there are actually self-balancing BST algorithms, such as the red-black trees and the AVL trees, which I will not discuss in this video. And the idea there is that once you insert or delete values in the BST, there is a way to rebalance the binary search tree to maintain the balancing so that you don't have a very skewed binary search tree. Okay. So let's go to tree traversal. So we earlier we mentioned that in the case of BST deletion, kailangan nating mag-traverse ng tree. Okay, so tree traversal is also known as tree search or walking the tree. And it's a form of graph traversal and refers to the process of visiting or checking the value of each node in a tree data structure exactly once. Okay? And there are different traversals, and they are classified basically by the order in which the nodes are visited. So there are two general types. One is depth first search or DFS traversal, and the second one is the breadth first search or BFS traversal. So under DFS, we have three types: in order, pre-order, post-order. So the main difference is that in order, you visit you traverse the left subtree of the node, you visit the node itself, and then you traverse the right subtree. In the pre-order, the order is that you visit first the node, and then you traverse the left subtree and then the right subtree. Post-order is visiting the left subtree, the right subtree, and then the node itself. Okay. So the breadth first search traversal is implemented using the level order. So in this case, when you traverse the tree, you display the values from top to bottom, from left to right. Okay. Okay. So let's look at the different the binary tree implementation in Python. So here's an example. As you can see, there's a data structure for the node. Okay, so we define the class node, and it has the left, right, and the data, which stores the key value, the left child node, and the right child node. Okay. So, and as you can see, we implement here the different methods of insert, search or find val, and the different traversals: in order, pre-order, post-order. And also here's an example of inverting the order of the binary search tree. So you just try this out, and so this is all for now. See you in the next video.